This is Professor Pelton. This is Math 155, chapter exponential function. This is part 1 of 2. Exponential function must keep one of these formats, either equation or function format that's specified here. What's important is the base number b. Okay, the base number b must be any real number that's positive, right? And it can't be 1, because if we keep multiplying by 1, it's just 1. It would be a constant function. It would not be an exponential, and you can't be negative either, because that would reciprocate between positives and negatives as the exponents change. So the idea here is the exponent is a variable. Okay, so look through here and we'll decide which ones are, in fact, exponential functions. So we look at these ones here. The first one has a real number, positive. That's greater than 1, so that's fine. Or I'm sorry, not greater than 1, but is not 1, so that one's fine. The second one is not fine. That's actually a quadratic, right? That's a quadratic function. So you have two problems. One, that's not a variable. Well, there's no variable in the exponent, and the base is not a positive constant. Other than 1. So, next one, that one's fine. You can add things and multiply by things in the exponent. That's fine. You got a constant base. That's not a variable when it's not 1. You're fine there. This one is not fine because you cannot have a negative base, because it would become negative, positive, negative, positive, negative, positive as you change the exponent. So that one's not good there. Okay, pause the video, try the student problems for yourself. Alright, for the student problems, the A is fine, and the C is fine, because the bases are both numbers that are real, that are not 1, and they are not negative, and the exponents contain a variable. This one is not good, however, because the base cannot be 1, because that would be a constant. 1 to any power is just 1, it's constant. And this one can't have a variable. Cannot be a variable, so the base cannot be a variable. It needs to be a constant number other than 1 that's positive. Okay? Alright, page 2. So in general, the exponent function has these characteristics. You can plug in any number you want to the exponent, positive or negative. However, no matter what you plug in, it's going to be 0 to infinity for the range, because no matter what you plug in, you cannot get a negative answer. You can get 0, right? Well, you can't get 0, actually. I'm sorry. You can get 0 to infinity, but not 0. So take any number you want, b to any negative number, right? This is the negative exponent property. So that gives me 1 over b to that number. Gives me a fraction. So as a result, I can get positive numbers, I can get fractions, I can't get 0, and I can't get a negative outcome. Okay? So if that b on the bottom is greater than 1, it's growth. If it is 1, it wouldn't be an exponential, it'd just be constant, because 1 times anything is 1. And then if it's between 0 and 1, thus a fraction, right, a proper fraction, then it's going to be decay. And it has a horizontal asymptote of y equals 0, and it has an inverse. Okay, let's graph a few of these and give them a try. So based on the bases, you should be able to decide right away if they're growth or decay. If not, do a table of values. So x comma y, x comma y. So do some very basic values of -2, -1, 0, 1, 2. -2, -1, 0, 1, 2. So this is 2 to the -2, which is 1 over 2 to the second power, which is 1/4. If you change it to -1, you just get a half. And then the 0 power is 1. To the first power is 2, and to the second power is 4. Okay, so go over to here. 1/2 to the negative 2 is 2 over 1 to the 2. We do the exponent rule of a negative. So that's 2 squared over 1 squared. Thus, the answer is 4. If we just change this to a negative 1, it just flips, so we get an answer of 2. Next one, anything to the 0 power is 1. Then we'll do the positive ones. If you plug in 1, you get a half. If you plug in 2, you get 1 squared over 2 squared, and thus 1/4. Okay, so let's graph those. At negative 2, I'm at a quarter. I'm at a half. I'm at 1. I'm at 2. I'm at 4. So we have a graph that looks like this. And then we're at 4. We're at 2. We're at 1. We're at a half. We're at a quarter. Okay. All right. My art skills might not be that great, but it's generally the idea. All right, so I can plug in anything I want. You can see from the x, so it goes forever left and forever right, but never gets to infinity. Okay. The range, it goes forever up, obviously. Okay. The question is, how far down does it go? Well, if you look at the table of values, okay, it goes 4, 2, 1, 1/2, 1/4. Next will be 1/8, then 1/16, 1/32. You continually get smaller, but you never reach 0. It's impossible. No matter what number you put in the denominator, you're not going to get 0. Okay. Over here, same thing. It goes forever left and forever right. There is no limitation to the x values I can plug in. However, same thing. The fractions get smaller and smaller, but you never get to 0. So it goes forever up, but on the low end, it's going down to 0, but doesn't get there. Because what we have is an asymptote. This asymptote is y equals 0. Same thing here. Asymptote of y equals 0. The invisible line we cannot cross. So, growth or decay, you should be able to tell by the base that this one is a 2. That's greater than 1, therefore that's growth. Also, if you read a book left to right, it goes up, doesn't it? Second one, it's a half. That's less than 1, but greater than 0. That's decay. Also, if you read a book left to right, it clearly goes down. Okay? Pause the video, try the student problems for yourself. Okay. So here, 3 to the x, we'll do an xy table. Do some basic values. Okay, so 3 to the negative 2 flips it over, gives me 1 3 squared, which is 1/9. If you change it to a 1, it's just going to be 1/3. Anything to the 0 power is 1. 3 to the first power is 3. 3 to the second power is 9. Go over to here, do the same thing. 1/3 power to the negative 2 is 1, I'm sorry, that's wrong. 3 over 1 squared, using the negative exponent property, which is 3 squared over 1 squared, thus 9. If I change this to a negative 1, it flips it and just gives me 3. If you plug in a 0, anything to the 0 power is 1. Plug in the positives. Plug in 1, I get 1/3. Plug in 2, I get 1/9. Notice again, just like the previous problems, the values flip in the tables for the y values. So at negative 2, I'm at a 9th. At negative 1, I'm at a 1/3. 0, I'm at 1. 1, I'm at 3. And 2, I'm at 9. Okay. On the other one, we're at negative 2, we're at 9. Negative 1, I'm at 3. 0, I'm at 1. 1, I'm at a 1/3. I'm at a 9th. Barring my art skills. It's approximately what they look like. I can plug in anything I want for the x values in either problem. Positive, negative, or 0 can be plugged in for x. And graphically, it goes forever left, forever right. For the range, however, it goes clearly up forever, and I can get any y value going up. But going down, it goes 1/3, 1/9, 1/27, 1/81. I can't get to 0 going down. I certainly can't get negative. So same thing here, 0 to infinity as far as output and graphical. So if you read it left to right, it's clearly going up here, and the base is greater than 1, therefore growth. On the right-hand one, B, it's clearly, if you read left to right, it's going down. Also, the base is less than 1 but greater than 0, therefore it's decay. So there's two ways to do things. In either case, as long as you can get that, that's what's important. Page 3. So in prior chapters we had transformations, but these are specifically transformations of the exponential functions. So these same rules still apply. However, instead of doing generic functions, it's specifically the exponential function. So the adding and subtracting is still vertical translations on the outside, and if it's in the inside, it's horizontal translation. Inside in this case is inside the exponent, so it's a little bit different. It's not inside a parenthesis like it would be the trig or an exponent, a quadratic or something like that. Reflections maintain the same. They still do reflections, although the inside this time is inside the exponent. And stretching and shrinking, otherwise known as scaling, same thing. Multiplying on the outside is vertical, multiplying on the inside is horizontal. Keeping in mind, anything that's in the inside is counterintuitive, and the order of translations, which is the order of operations, still maintains the same. So 1, 2, 3, 4. You can still look back at the cheat sheet that's posted for the prior chapters. Order of transformations must be horizontal translation must come first. Then you have your scaling, which can be stretching or shrinking. And then you have your reflections, X or Y. And then lastly, your vertical translations. Okay, so they must happen in that order, and there can be two flavors of each, horizontal or vertical. Okay, all right, let's try some problems. Okay, so if you graph 2 to the x, which we did prior, you're going to get this graph. And you just need a few points to make this applicable. So we get the standard point 0, 1, because you plug in 0, you get 1. You get this point here, which is 1, 2. The next point is 2, 4. And the next point is 3, 8. You can go back and verify those for yourself, or just regraph it if you want. What's important is we're going to take the parent and graph from there. So we have negative 2x minus 2 plus 1 is the new function they gave us. So this 1 is on the outside, so that affects y. So that is a vertical translation. So we're going up here. So if it's inside the exponent, okay, that's going to be a horizontal translation. And the negative on the outside is a reflection, obviously. It's multiplying by a negative 1. On the outside affects y. So if you change your y value, you want over the x-axis reflection. Okay, but again, there's an order here, right? Horizontal translation happens first, then scaling, which we don't have in this problem. The reflection happens second, and the third thing to happen is the vertical translation. Okay, if you look back at the list. Okay, so we'll take the each coordinate here and do each of these things in the progressive order. So if we take the coordinate 0, 1, we have to move it over 2. So we have to take the coordinate 0, 1 and move it over 2. Okay, that's step 1. So that is the original. Right, we moved it over 2. And then it has to reflect over the x-axis, so it's going to go down to here. And then it has to go vertical translation of up 1, so it's going to go to here. Okay, so that point is done. Alright, the next coordinate in the list is 1, 2. And we'll follow the same order. We need to go horizontal translation of right 2. Because again, if it's minus 2, it actually has to be in the opposite direction, because in the exponent or inside the parentheses is counterintuitive. So the next thing is reflection over the x-axis. So I go down to here. And then it says vertical translation up 1. So we go to here. Alright, so get rid of these points. Okay, so the next point is, we did this one, we did this one. The next point is 2, 4. So we go to 2, 4. So in the order of things here, we have to go right 2. We have to reflect over the x-axis. And we have to go up 1. Okay. Alright, last point. So the last point is 3, 8. So we go to 3 and 8. We have to go right 2. We have to go over the x-axis. And we have to go up 1. Alright, so now we need to connect the dots. So keeping in mind, our original asymptote is y equals 0, right? So now, since we went up 1, in our translation, it's now y equals 1. So we make our graph. It's going to be like this. So I can go forever left and forever right. However, my range, it goes down forever, but it goes up to positive 1, but doesn't get there. Okay? Pause the video. Try the student problem for yourself on the next page. Okay, student problem again. We'll take the parent function 2 to the x, and we'll get some standard points of 0, 1, 1, 2, and 2, 4, and 3, 8. Okay, so we write the new function down here. 2 to the negative x plus 1 minus 1. So that minus 1 is a vertical translation down. The plus 1 inside the exponent is a horizontal translation. Since it's plus 1, it's actually going to go left. Then we have this negative right here, which is a reflection. So since it's the inside, it changes x. If you change your x value, you went over the y axis. Okay? So according to the order of operations, or the order of transformations, which is the same thing, that happens first, that happens second, and that happens third. We don't have any scaling in this one, so that is just eliminated from the order. Okay, so we'll take our points. We'll take our point 0, 1 first. And we have to horizontally translate left 1. Then we have to reflect over the y-axis. Then we have to translate down 1. Okay. Alright, next coordinate is 1, 2. So we'll put our 1, 2 on there. According to our list of things, we have to translate left 1. We have to reflect over the y-axis, but it's already on the y-axis, so that means we don't do anything. And we translate down 1. Okay. Next one is 2, 4. So our order of things says translate left 1, reflect over the y-axis, and translate down 1. Okay, last coordinate 3, 8. Okay, order of things says to move left 1, reflect over the y-axis, and translate down 1. Okay, so the last piece to complete the graph is think about asymptotes. The original asymptote was y equals 0 because we couldn't get 0 or less, but we moved down 1 vertically. So now if we go down 1 vertically, it's now y equals -1. So we can complete our graph now. which is clearly the decay graph. So I go forever left and forever right. I can go down to -1 but not get there, but I can go up forever. So that's our domain and range. All right, let's try the next problem. Okay, last problem. Standard 2 to the x. We get our points of 0, 1, 1, 2, 2, 4, and 3, 8. 3 to 4 coordinates is fine for any exponential function when doing the transformations. Obviously, they're not going to be the same every time because 3 to the x and 4 to the x and 5 to the x will all have different coordinates each time, but just do the ones that are nice whole numbers. Okay, so we have a 1/2 times 2 to the x this time. So all we have is this half in the front. So if you're doing multiplication, that must be scaling. Since it's on the outside, it's y. So that's a vertical scaling, right? Which it's only a half. That's going to be a shrink. If it was a 1/2 in the inside, which is the exponent, it would be counterintuitive. It would be a stretch, but since on the outside it's straightforward, it's a shrink. So we're only shrinking vertically. So if I take my first point, 0, 1, okay, the y value is 1. So I go to a half as a result. The next coordinate is 1, 2. The y value is 2, so I go to 1, 1. The next coordinate is 2, 4. The y value is 4, therefore I go to 2. The last coordinate is 3, 8, therefore I go to 3, 4. So when you do each of these things, it only affects one value, x or y. So it only affected the y value here. Okay. So my graph goes like so. It's because my original asymptote is y equals 0. But I didn't translate up or down. All I did was shrink it down. So it's the same graph, just shrunk down. So since I did not translate up or down, I still have a y equals 0 asymptote. So I go forever left and forever right. I go forever up, but I'm only going down to 0, but I can't get there. That is the end of part 1.